Welcome all of you to the video lecture series on computational fluid dynamics, development, application, and analysis. The present lecture is on computational fluid dynamics on a staggered grid. The details of this video lecture can be found in the chapter 9 of the companion book, Introduction to CFD, Development, Application, Analysis. For this video lecture series on first course in computational fluid dynamics, which is presented in the YouTube channel CFD Made Easy. I'll be presenting 6 different topics. So I started with introduction and essentials. This is like the part 1 of this lecture series, where I talked about the introduction to CFD, essentials for CFD. So this topic talks about the very essential topics in fluid dynamics, heat transfer, and numerical methods, which are needed to learn CFD. So this builds the foundation for the first course in computational fluid dynamics. Thereafter, in the part 2, I had covered the computational heat transfer, where when we went into heat convection, we have considered problems where we do not have to bother about fluid flow. So this problem corresponds to a prescribed fluid flow based heat convection problem. So the conduction is like building the first component of a computer program for the fluid dynamics, which corresponds to the Navier-Stokes solver. And so we started component by component development, starting with conduction. Then we had considered the combination of conduction and advection for convection. So in this computational heat transfer, we were involved only with one of the conservation laws in fluid mechanics, that's the energy conservation law. We have avoided the use of mass and momentum conservation law for heat convection by prescribing the flow. And then in the part 3, which corresponds to both fluid dynamics and heat transfer, we are into the last topic, that is computational fluid dynamics on a staggered grid. So this topic is presented in 2 parts. So in the previous part that I present, in the part 1 that I presented in the previous lecture, I have covered 3 different subtopics. I started with challenges in CFD development, where I have mentioned 3 different challenges in the beginning of the CFD development, which corresponds to non-linearity in the advection terms of the Navier-Stokes equation. The second was there is no explicit equation for pressure. And the third, there is an issue of pressure velocity decouplings when people started solving the Navier-Stokes solver. So these were the 3 challenges which were encountered in the beginning of CFD development. And then I talked into one of the first remedy to pressure velocity decoupling, which is called a staggered grid. And then I had presented the physical law and discrete math-based finite volume method for a staggered grid. Note that the novelty of this video lectures and the book, companion book, is the finite volume method is presented involving more of physics and less of maths, where from the conservation laws which are used to derive the differential equations in undergraduate fluid mechanics and heat transfer, the same conservation law which is applied to a control volume is used here also for CFD to derive algebraic equations instead of differential equation in undergraduate courses. However, to derive the algebraic equations for a computational course from the conservation law, we need to use discrete math, where we need to use certain approximation that was presented in the previous lecture. So we are into the part 2 of this topic 6, whereas in this lecture, I'll cover the flux space solution methodology on a uniform grid using semi-explicit method. I'll present this flux space solution methodology on a uniform grid using semi-explicit method. So I'll start with philosophy of pressure correction method, and then I'll move on to semi-explicit method. When in conduction and convection, we have 2 types of method, fully explicit and fully implicit. Whereas when we go to solve the momentum and mass conservation equation together, we cannot adopt fully explicit method. So we use a method which is somewhere in between. It's more of an explicit as compared to implicit. It is called a semi-explicit method, which I'll introduce little later. And finally, I'll present the solution algorithm and insert an example problem corresponding to the solution method. So in the part one, I had mainly presented the physical law-based finite volume method on a staggered grid. After starting with the challenges and presenting the staggered grid. And in the part two of the topic on CFD for a staggered grid, I'll be focusing on the solution methodology. So let us start first with the philosophy of pressure correction method. The need of this philosophy is because I had presented in my previous lecture when I talked about the challenges in CFD development, that there is no explicit equation, there is no explicit conservation law for pressure. We have conservation law such as momentum conservation, where we have term like rate of change of velocity. We have a conservation law like energy equation where we have rate of change of enthalpy. So from rate of change of momentum in the momentum conservation, you get an idea that we can use momentum conservation to create a movie for velocity. In energy equation, when we think of rate of change of enthalpy, we get an idea that from that statement, we can get a movie to capture the temperature variation in space and time. However, we do not have any conservation law which has statements like rate of change of pressure. We have mass conservation law, and in fact, mass conservation law is a function consists of the density, the normal velocity, and surface area. The mass conservation law, in fact, do not involve pressure in any way. The pressure appears in the momentum conservation, but not as a variable in the mass conservation equation. So this is what I mean, that we do not have an explicit law for mass conservation, and it's just that we are left with mass conservation law as a to recover as an and to come up with an algebraic formulation for pressure. So one of the biggest challenge in the development of history of development for Navier-Stokes solution computationally in CFD has been how to convert the mass conservation equation as an algebraic equation for pressure. So in this regard, certain philosophy was presented, and using this philosophy led to development of certain algebraic formulations, which led to the solution of mass conservation equation to recover pressure. So I'll start with the philosophy, and then I'll present the mathematical formulation which follows those philosophy for a semi-explicit method. So the remedy to no explicit equation for pressure is philosophy of pressure correction. This philosophy is used to come up with mathematical formulation or algebraic formulation to obtain pressure from mass conservation equation. Note that when you think of mass conservation law for an incompressible flow, and this video lecture is mostly on CFD for incompressible flow. So you need to note that for incompressible flow, in fact, the unstudied term in mass conservation law, the unstudied term in mass conservation law consists of rate of change of density. And for an incompressible flow, it is 0. So you end up with a steady state form of the mass conservation law for an incompressible flow. So the challenge is much bigger for CFD for incompressible flow as compared to the CFD for compressible flow. Because for CFD for compressible flow, we use mass conservation equation to create movies for densities, and pressure is recovered from another constitutive law like an ideal gas equation, pressure density relationship. So I'll present the philosophy of pressure correction method through this slide, where you can see, let us consider this control volume, and we start our simulations from the initial condition. I have mentioned in my previous lecture that the initial condition and boundary condition gives you the first picture of your fluid dynamic movie. And from the data of the first picture, we create the data of the second picture. And from the data of the second picture, we create the data for the third picture. So this way we create picture by picture for velocities, pressures, and temperature to create a fluid dynamic movie for velocities, pressures, and temperature. So let us suppose you know the field variables corresponding to velocities and pressure from initial condition and boundary conditions. So using the initial condition and boundary condition, whatever velocities and pressure you have, using those, let us suppose you follow a fully explicit method where you take the values of velocities, pressures from previous time step, and then whatever velocities you have obtained. If you are using a staggered grid, note that you have you obtain the velocities on the vertical surfaces, u velocities, and v velocities on a horizontal surfaces. So once you solve the momentum equation as in a fully explicit form, let us suppose you obtain velocity distribution at the faces in a staggered grid, using which you can calculate the mass fluxes by multiplying by density. So let us suppose in a staggered grid you have UW here. So UW, if you apply the X momentum conservation, fully explicit, let us suppose you have obtained first, let us suppose UW, and then you multiply by rho, you got mass flux entering from the left surface is 1 kg per meter square second, and from the bottom surface also for v velocity you have applied y momentum conservation, and you have obtained the predicted the mass fluxes as this. Okay, so let us suppose using a fully explicit method and applying the X momentum conservation law on a staggered U control volume and Y momentum conservation law in a V staggered control volume, we have obtained first these normal velocities, and then you multiply it by density to obtain the mass fluxes. So by using the fully explicit method, you let us suppose you have got this mass fluxes. Now you can see that if you apply the mass conservation law, you can see the mass conservation law is not obeyed. So if you use a fully explicit method, it so turns out that from momentum equation by fully explicit method, you end up with velocity distribution which do not obey the mass conservation. Now, by looking into this mass flow rates, you get an idea that let us assume that the surface area is unity 1 meter square. So when you multiply this mass fluxes with the surface area to calculate the mass flow rate, so by assuming the surface area is unity, we can see that the total mass flow rate going out of the control volume is 4 kg per second, and the total mass flow rate which is entering the control volume is 2 kg per second. So you can see that there is a net mass outflux with mass outflux which is mass flow rate, net mass flow rate leaving the surface of the control volume is corresponding to 4 kg per second minus 2 kg per second, that is 2 kg per second. So when you have more mass going outside the surface of the control volume, and let us assume that you have a in this philosophy, what the idea is based on whether the net mass outflux is positive or negative. Let us suppose you are given a freedom to tune the pressure inside this control volume. So in this case, if I ask you a question that if more mass is going outside the surface of the control volume, then if you have the freedom, let us suppose you have like a radio knob, you can control the pressure inside this control volume. Let us suppose this right now this pressure corresponds to 1 atmosphere. So if more mass is going out, what you would, whether you will increase the pressure or whether you decrease the pressure. Now let us suppose if you consider a square region having a fluid, and if you have a control to let us suppose vary the pressure. If you decrease the pressure, the decrease in the pressure will lead to more fluid rushing inside the control volume. If you increase the pressure, then less fluid will come inside the control volume. In the present case, you want your mass outflux is positive, and you want to balance the net mass flow rate leaving the surface of the control volume. You want for mass conservation, net mass flow rate leaving across the surface of the control volume is 0. So now in this case, more certain non-zero mass flow rate is leaving the control volume. So to control it, philosophically, you would like to reduce the pressure so that when you reduce the pressure, this 1 kg per meter square second will increase, and you wish and hope that the increase of the inlet mass flow rate will be able to balance the net mass flow rate, the mass flow rate leaving, so that the net mass flow rate leaving the surface of the control volume, net mass outflux will become close to zero. So with that philosophy, let us suppose you reduce the pressure of the control volume. Now to reduce the pressure of the control volume, we define a term which is called as pressure correction. So we are it's like we are controlling the pressure, and let's suppose if you reduce the pressure, and this pressure which you have reduced is like you are doing some correction. So this pressure correction, let us suppose since you are reducing, so it will have a negative value. So let us suppose it's minus 0.5 atmosphere. So if you have reduced the pressure by minus 0.5 atmosphere, then 1 minus 0.5 you will get 0.5. So this is corresponding to 0.5 atmospheric pressure. Note that this is like a first, this is not corresponding to a real world situation. This is a numerical situation, and this picture that I am showing you corresponds to, let us say, the first iteration of our solution for pressure. Note that since we do not have an explicit equation for pressure, and somehow we are trying to use the mass conservation law with certain philosophy, we have to pay a price. The price for no explicit equation for pressure is, the price for no conservation law which talks about rate of change of pressure is, we have to obtain a solution in an iterative manner. Note that in the previous topic, when you were using explicit methods, you had only one loop corresponding to time. But when you go to solve mass and momentum conservation together, even if you are using an explicit method, you have one iterative loop corresponding to pressure or pressure correction. Okay, so this picture that I am showing you, it is never possible in real world situation, because in real world situation, mass conservation at each and every time instant in a flow field is always obeyed. So what I am showing you is like a numerical picture. You are doing certain computations, and from those you're getting some number generation corresponding to physical variables. And so this is corresponding to the first iteration, where we are using a philosophy that if the net mass outflux is positive, then you reduce the pressure so that more mass come in and the mass outflux is reduced. If more mass outflux is negative, then you will increase the pressure. So in this case, in the first iteration, you have reduced the pressure. But when you have reduced the pressure, what is the guarantee? Because when you reduce the pressure, now this inflow mass flow rate, the mass flow rate which is entering the control volume will increase. Now, so when you reduce the pressure, let us say the incoming mass flow rate have increased by +2. So 1 + 2, you will get 3 kg per meter square second as the mass flux on the left surface and the bottom surface. And when you reduce the pressure here, let us suppose the mass flow rate leaving the surface of the control volume gets reduced by -1 kg per meter square second. So you get a new mass flux which is given as this. So by reducing the pressure, you wished and hope that more mass flow rate entering will increase and you will have net mass balance. But it so turned out that now more mass is entering inside the control volume, and now the net mass outflux is negative. So now in this case, you would like to increase the pressure so that because you want now the mass outflux to be, you want to reduce the incoming mass flow rates. So let us suppose now you tune the pressure, you increase the pressure by 1.5, which is pressure correction is 1.5. and you get 0.5 plus 1.5, that is 2 atmosphere. This is the new pressure. So this way I am showing you philosophically that this is the first iteration, this is the second iteration. In the next slide, right now here it looks this philosophy looks too much arbitrary, but in the next slide I will show you some mathematical correlation in terms of certain functions, and that whose derivation will be presented in the later slides. So using the basic idea of the relationship between the net mass outflux and the pressure, we have an idea that if the net mass outflux is positive, we should reduce the pressure. And if the net mass outflux is negative, then we should increase the pressure inside the control volume. So using this philosophy, in the first iteration, I have mentioned, here I will show you the first iteration which I presented through an animation in the previous slide, along with a solution algorithm. So using the data from the previous picture, if you are using a fully explicit method, you can obtain actually the velocity that you are obtaining or the mass fluxes that you are obtaining. Note that they, in any iteration, they are not the true value for the next time step. So we will call this as star values. So using the previous time level values of velocities and pressure, if you use X momentum conservation law, you can obtain UP and UW. If you use Y momentum conservation law, you can obtain VP and VS. So once you have obtained this, you multiply it by density. And so using a fully explicit method, this is a tentative solution algorithm for this for the Navier-Stokes solver. So in the first step, using fully explicit method, you end up with this type of mass fluxes. Now this mass flux this mass flux, we'll call it as a predicted mass flux due to the fact that they are not obeying the mass conservation law. So they are just some predictions. We follow an approach which is called as predictor-corrector approach. So this is the first iterations. So the predicted value denoted here by the star mass flux. Using the star mass flux, you can obtain, you can multiply by the surface area, and you can calculate the mass flow rate on the east surface, west surface, north surface, south surface, and you can calculate net mass source. So from the predicted velocities, you are obtaining the predicted mass flow rate and mass source. Now let us suppose in this case, you can see if we assume the surface area is unity, you multiply this mass fluxes by the surface area of 1 meter square, and you find that the net mass imbalance of the first iteration, the superscript 1 representing the first iteration, the net mass imbalance is 2 kg per second. Okay, so in the second step of the solution algorithm, using the mass fluxes, the mass flow rate and net mass imbalance is obtained. If the net mass source computationally, the computer doesn't understand what is zero, you define what is called as convergence tolerance. So let us suppose you define 10 to power minus 3 as zero. So let us suppose if you say epsilon as a convergence tolerance is 10 to power minus 3. So we compare this mass source, if it is less than the convergence tolerance. If it is less than convergence tolerance, it means it's a very small value. So it is almost zero. So if it is almost zero, then whatever velocities and mass fluxes that you have predicted becomes the true velocities and pressure for the next time step. However, this normally doesn't happen, and what you find is that you have to go to the next step and you have to continue. So in the next step, based on the mass imbalance, we right now I'm showing you through the philosophy a symbolic expression. We have a symbolic expression from the philosophy which says that if the net mass imbalance is SM star is positive, pressure correction should be negative. If the SM star is negative, then the pressure correction should be positive. Which means when I say it's negative, I means when more mass is going out, then the pressure we should decrease the pressure, which means pressure correction should be negative. If less mass is going out, we should increase the pressure, so pressure correction should be positive. So from the philosophy, here I am presenting that there is a negative correlation between the pressure correction and mass imbalance. This is a mass source or mass imbalance. So we need a functional relationship. So we need a mathematical equations whose derivation I will show you later, of pressure correction as a function of mass imbalance. So let us suppose we use such type of equation, and by using this mass imbalance, you obtain pressure correction as minus 0.25. So in the previous slide, I have not mentioned from where you obtain this value, but in this slide, I am making it little more clear, saying that later on I will show you, we will derive an expression between pressure correction as mass imbalance with a negative correlation between the two. And from that equation, we obtain the pressure correction as this. Once we obtain, so this is the pressure correction which is obtained in the first iteration. So for the second iteration, now the pressure, the pressure, so you have a predicted pressure which is 1 atmosphere. You have in the first iteration, you've obtained pressure correction as minus 0.5. So the true value is equals to the predicted value plus correction. So pressure for the next iteration will be the previous iterative value plus corrections. So if you add this to 1 minus 0.5, so that you will get minus 0.5 atmosphere for the next iteration. Okay, so in this fourth step, you have obtained pressure correction as a function of mass imbalance. So you have a formula where you use this mass imbalance and you obtain a solution as this. And using this, you obtain the new pressure by adding the pressure correction with the previous iterative pressure. Now, along with this equation, there is a second equation which will also be presented a little later, which correlates the mass flux correction as a function of pressure correction. Okay, so if you know the pressure correction of all the grid points or all the yellow circles, using those pressure correction, if you use this formula whose derivation I will present in the later slide, you can obtain mass flux correction. So let us suppose for this iteration, using this pressure correction, you obtain mass flux correction as this. So now it shows that on east and north surface, mass flux correction is minus 1, and on the negative surface, west and south, it is 2 kg per meter square. So on the negative surfaces, the mass flux is increasing. These corrections are, for the next iteration, the mass flux that you will obtain will be summation of this mass fluxes with the correction. So this negative spaces, you have 1 kg per meter square. So if you, on the negative surface, you have mass flux correction is plus 2. So 1 plus 2, now you will get 3 kg per meter square, which is shown here. And for the positive surface, the previous iterative value was 2 kg per meter square, and the mass flux correction is minus 1. So 2 minus 1, it will be 1 kg per meter square. Okay, so I am showing you a solution algorithm step by step, where we know that we use two expressions: pressure correction as a function of mass imbalance, and second equation, mass flux correction as a function of pressure correction. And using this two expression and using this solution algorithm, in step 6, you have come to the end of the first iteration. Then at the end of first iteration, go to step 2. When you go to step 2, then in the step 2, basically you multiply this mass fluxes with the surface area. Here in this case also, let us assume that the surface area is unity. So this will become total 6 kg per second is entering, and 2 kg per second is leaving. So mass source will be 2 minus 6 to minus 4 kg per second. So when you go to step 2, you first calculate the mass flow rate and the mass source, which is now, earlier it was plus 2, here now in second iteration it is minus 4. So then you go to the next step. The next step says if the mass imbalance is less than convergence tolerance or close to 0, which is not the case here. So we will continue. So then we will use this mass imbalance on the right hand side and we'll obtain the pressure correction. So let us suppose when you use the formula, you got the pressure correction as plus 1.5. So pressure correction is plus 1.5. Note that earlier when the mass imbalance was positive, pressure correction plus 2, it was minus 0.5. So when it was plus, the pressure correction is negative. Here, mass source is negative, pressure correction is positive, and I had indicated that they have a pressure correction and mass imbalance have a negative correlation. So using this formula, you got, let us say, pressure correction is this. So for the third iteration, you can add this pressure with the second iteration with pressure correction. So you add 0.5 plus 1.5. So for the third iteration, the pressure will be 2 atmosphere. So there will be a third iteration. So this way we continue with iteration by iteration. After obtaining the pressure correction, using this pressure correction, you calculate the mass flux correction. So once you calculate the mass flux correction, now let us suppose for the second iteration you got on the positive faces is plus 3 and on the negative faces is minus 2. So this on the positive faces it will become 4 kg per meter square second, and on the negative faces it will become 3 minus 2, which is 1 kg per meter square, which is again not obeying the mass balance. So you will do third iteration. So this way you keep doing iteration by iteration till you reach to a situation, and fortunately we reach to a situation where the mass balance approaches towards zero, and so once this iteration is complete, you obtain the mass fluxes, because note that you are following a predictor corrector approach where first you are predicting this mass fluxes, and later on when you add this star values with prime values, you are getting the updated values of mass fluxes, and finally you end up with those mass fluxes which obeys the mass balance. Those mass fluxes and those velocities, when you divide the mass fluxes by the density, you can obtain the velocities. So once the mass conserving mass fluxes you obtain, from that whatever velocity you obtain are the true velocity for the next time step. So note that from the data of the previous picture of the velocities and pressure distribution, if you follow an explicit method, you have to use an iterative method to obtain the correct velocities and pressure. Otherwise, by fully explicit method, if you the velocities that you obtain does not obey the mass balance. So from the philosophy here I had presented that the solution of mass conservation equation for pressure is iterative in nature, and note that this is coupled in a sense because you are following a predictor corrector approach where you first obtain the star values which are predicted value, then you use certain equations. Note that here there are two equations which are extremely important: pressure correction as a function of mass imbalance with a negative correlation, and mass flux correction as a function of pressure correction. Later, in the later slide, I will show you the derivation of these two expressions. Right now, I am presenting it as in a functional form, but later on, I will show you a detailed expression that we will derive. This is probably one of the most, I would say, key and difficult concept in this course on computational fluid dynamics. So after presenting the philosophy, I will, for a semi-explicit method, we will derive the expression for the pressure correction as a function of mass imbalance and mass flux correction as a function of pressure correction. As I had mentioned earlier that we follow a predictor corrector approach. So it's like Z is equals to X plus Y, where let's suppose X is the predicted value, Y is the corrected value, and Z is the true value. So true value is equals to predicted value plus corrected value. Our true value is the value corresponding to the new time step, that is n plus 1. The predicted values are presented here by a symbol star. The corrections are presented here by prime. And note that so this is like a Z. Z is original proposition. So in the original proposition, we consider in a semi-explicit method pressure as implicit. So all terms explicit except pressure. So in the semi-explicit method, we consider, when I say all terms, I mean diffusion and advection, which for X momentum equation, diffusion is net viscous force is acting in the X direction, advection is net X momentum flow rate leaving the surface of the control volume. So in a semi-explicit method, we have another method which is called as semi-implicit method, where we considered advection diffusion as implicit, and later on, by deriving the equations for correction, we use certain approximation which convert that implicit method into a semi-implicit. But in a semi-explicit method, note that the original proposition for obtaining the velocities at new time step, this is from X momentum conservation, this is from Y momentum conservation, all the terms are explicit, all these terms have a superscript n except pressure. And as I had mentioned earlier, that in mass conservation, we do not have any explicit approach, because while applying the mass conservation, whatever velocities we have obtained from the momentum conservation, those have to necessarily obey the mass conservation. Okay, so we always need to take mass conservation as implicit, because this is like the final test which decides whether a velocity field is correct or not. So we always need to take the mass conservation equation, algebraic equation, as implicit. And as I mentioned, that we solve this using a predictor corrector approach, where we do predictions and corrections of three variables: velocities, which on a staggered grid are presented at the phase center as shown here for a staggered grid. So we have predictions u star for velocity, u star, v star will be prediction, correction will be u prime, v prime. Similarly, we will have mass fluxes, mx star, my star, mx prime, my prime, and we'll have pressure predictions and correction, p star and p prime. And we'll have expressions like true value, which corresponds to the time level n plus 1, is equals to the star value plus prime value as shown here. So for velocity, this is like velocity true value for the next time step is equals to the predicted value plus correction. This is for u, this is for v. Similarly, we have for mass fluxes, we'll have mx for east and west vertical surfaces. The true value is equals to the star predicted value and the prime correction value. So this is for the east and west, this is for north and south. So note that in the semi-explicit method, I will show you, we'll derive equations for predictions and correction for three variables. First, velocities, which are normal velocities for a staggered grid. These velocities are acting normal to the surface area of the mass conservation. Then we'll predict and correct. So we have m star, m prime. So you note that we not only have u star, u prime, but we also have m star, m prime. And finally, we have pressure, prediction, and correction. So here I have shown you prediction plus correction as the true value for velocities, mass fluxes, and pressure. As I had mentioned, that we do not get the true value in one calculation. We have to do iterations. And in computation, when we do iterations, then we use this expression in a new way. The way is u star new value. So this right hand side, we do not tag it with n plus 1. Although originally we defined in this way, but when you implement it numerically, the fact that when you use for the first time, like which we call as first iteration, you end up with velocity distribution which does not obey the mass balance. So what we do every time, once we have calculated the left hand side, the right hand side we write it like this, as we do in any computation. New value of u star is equals to old value of u star plus u prime. Similarly, new value of v star is equals to old value of v star plus v prime, and similar term for mass fluxes and pressure. So the velocity the pressure and velocity correction is continued iteratively till a velocity field that leads to zero mass source is obtained. So once you get the new values of U star and V star, and using new values of U star, V star, the new value of M star that you get, if those new values are M star, net mass source is zero, then only the right hand side of the above equation, then only the right hand side, which means the summation of these two, becomes the velocity, mass flux, and pressure for the next time step. So note that while implementing, we use this equation always where the right hand side we do not directly equate to n plus 1, but the right hand side we equate to a new value of this new value of U star for the summation of these two, new value of V star for the summation of these two, and new value of pressure from the summation of these two. I'll present this semi-explicit method in two steps. First step, which is called as a predictor step, which is presented here, and the second step, which is a corrector step. In both the steps, as I mentioned, there will be three variables which will be presented. Prediction of, like in this predictor step, prediction of velocity, prediction of mass fluxes, and and in the corrections also, we'll present the equations for the velocities, mass flux correction, and pressure correction. So for the velocity prediction, the idea is something like this, that if you have a formula z is equals to x plus y, so you have already know that your original proposition was where you had pressure in a semi-explicit method, pressure was considered as an implicit. So that was like Z. Now, so if this pressure is n plus 1, then here you have un plus 1. So that is like Z. Now, when you change the explicit pressure to explicit, in the original proposition, this pressure had superscript n plus 1. But when you made it explicit, because you have a starting trouble. In the original proposition, this were at n plus 1, which is at new time step. And the fact of the matter is you don't know the pressure of the new time step. So you have a starting trouble. So to get started, what you are doing is you are using the previous time level pressure. And when you're using a previous time level pressure, the left hand side no more remains as n plus 1. So now it becomes star values. So now you can see all the terms on the right hand side, it has a superscript of n. So it is like a fully explicit. So if this is, all this expression is like a fully explicit. This is from x momentum conservation, this is from y momentum conservation. So if you use a fully explicit, you don't get un plus 1, vn plus 1, but you end up with u star and v star values, where you obtain this diffusion, which is corresponding to the viscous forces, and reduction, which corresponds to the momentum flow rate, by using diffusion fluxes, viscous stresses, and for advection, it is momentum fluxes, where this phi is u for x momentum and v for y momentum. And the fluxes for the velocity prediction to calculate u star and v star, you calculate advection fluxes using certain advection scheme, which I had introduced in the previous topic. For a uniform grid, I had mentioned that for the various schemes that covered first order of wind, second order of wind, quick and central difference. So for those three schemes, I had presented a general expression for a uniform grid, where I have presented certain constant weights W1, W2, W3, where W1 is the weight of the downstream neighbor, W2 is the weight of the upstream neighbor, and W3 is the downstream, upstream, or upstream neighbor. So using those formulations from the previous topic, this was presented in a topic on computational heat convection. We calculate the advection flux, which corresponds to a momentum flux for the momentum conservation, using certain advection scheme. So based on one advection scheme, this W1, W2, W3 are decided. And then diffusion flux. Note that this advection flux and diffusion flux both are considered explicit. And because we are in the predictor step, we are considering all the terms as explicit. In the original proposition for semi-explicit, pressure was considered as implicit, but in the predictor step, we had taken pressure also as explicit. Other than the advection flux and diffusion flux, when you apply momentum conservation, because in momentum conservation, you also need mass flux, because the product of the mass flux with velocities gives you the momentum flux, which appears in the momentum as advection term. So to calculate mass flux, I had mentioned in my previous lecture when I presented physical law-based finite volume method on a staggered grid, that in a staggered control volume, to calculate mass fluxes, this is for the green square control volume, green control volume, and this is for Y momentum. I've shown you a red control volume. So to calculate mass fluxes for those control volumes, I had mentioned that we had to do linear interpolation, which is shown here for a uniform grid. So after presenting the advection flux, diffusion flux, and mass flux, which appears in the momentum conservation, now the mass flux, as I mentioned, it also appears in the mass conservation. So if you apply it to yellow control volume, where you don't have to do any linear interpolation, these are the mass fluxes. So the velocities you have already predicted, you've already got U star and V star. So in the previous slides, using here, that was from we have taken this mass fluxes as explicit, because I had mentioned in the previous topic that we avoid the nonlinearity at the advection term by taking this mass fluxes as explicit. So note that the mass flux appear in the momentum conservation as well as mass conservation. However, the time level associated with mass flux is explicit for momentum conservation as shown here as superscript of n. But when you go to mass conservation, it is considered as implicit. So the predicted values, not the previous time value pressure mass fluxes is used to calculate the mass source. So the new predicted values, the predicted mass outflux is used to calculate predicted mass source. So this is the expression. So in the previous slide, I had shown you the velocity prediction. In this slide, I'm showing you the prediction of mass fluxes. So after predicting U star, V star, and MX star, MY star, we go to a corrector step. And so this is like the original proposition of a semi-explicit. And as I said, that we have a starting trouble. We don't know the pressure of the next new picture on next time step. So to get it started, we take it what is available to us. What is available to us is that we always know the pressure of the previous picture. So when we take it explicit, then this left hand side no more remains the true velocity for the new time step, then it becomes a predicted value. This is like a fully explicit method based velocity. What you obtain, it's a star value. So this is like Z, this is like X, and so because original proposition equals to prediction plus correction. So now if you want to derive an equation for correction, Y will be equal to Z minus X. So if you subtract these two equations, you will get UN plus 1. So if you subtract these two equations, you will get rho delta Vp Up n plus 1 minus Up star. If you take this term on the left hand side, and this two term will cancel down. This two term will cancel down. And if you take this rho V, this is the volume, which is the denominator. If you take it to the left side, you get rho into volume divided by delta T. This UPN cancels down. This diffusion also cancels down when you subtract these two equations. And here you get Pn plus 1 minus Pn for the node for the pressure at yellow circle P, and this is at E. So when you subtract this two, know that the advection and diffusion term completely disappears, and then you end up with an equation like this, where un plus 1 minus u star, this is called as u prime. This is the definition of the velocity correction. So this is the velocity correction, and the difference, the this difference is the pressure correction. This is the pressure correction of node P. This is the pressure correction of node E. So from this, note that you are getting an equation for velocity correction as a function of pressure correction. So here, if I want to write an expression for UP prime, then I take this delta T on the right hand side, and I have equation like delta T divided by rho into volume. Now the volume of the control volume, staggered control volume, is for a uniform control volume. This height of the control volume is delta Y. This distance is the distance between the two yellow circles. This is the yellow circle corresponding to P, and this is E. This distance is delta XE. So this volume is equal to delta Y into delta XE. So when you take this volume to the denominator, when you divide by the volume, that is delta Y into delta XE, this delta Y cancels down from the numerator and denominator, and you end up with an equation which is UP prime is equals to delta T by rho. This is the surface area divided by volume, gives you a length scale delta XE. So this is the expression that you get for the U velocity correction. Now when you multiply this by density, you get mass flux correction. So this mxc prime is equals to rho into UP prime, and you get an expression like this, which is equal to minus delta T E prime, pressure correction of the east neighbor, minus, note that the pressure we define here. So the mass flux correction corresponding to this. First you have obtained UP prime at this grid point, at this node or at this pixel, and then you've obtained MXC prime here. Now this MXC prime is a function of P prime here and P prime here divided by the distance between the two yellow circles, which is delta XC. Similarly, if you consider to get a correct V velocity correction, we start with original proposition for V velocity in a semi-explicit method where pressure is implicit as shown here. Then when you make it explicit, we get V star. This is like Z, this is like X. Then when you obtain Y, you take Z minus X, which is for correction as shown here. Here again, you end up with this V prime velocity, V velocity correction. This is P prime and this is Pn prime. And here the volume of the control volume, which is given here, the volume is equal to delta X into delta Yn. So when you divide this, the surface area divided by volume give you the length scale. So here note that you got V prime, and then when you calculate the mass flux, so the Vp prime or M, this calculate the mass. When I say N, I mean if you consider this is a PP. So if you take the PP control volume, this is the north surface. So this is MYN prime. This MYN prime. To calculate MYN prime, you need the pressure of PN prime and PP prime. So to calculate the mass flux correction, note that in this control volume, the pressure correction is involved at this point and this point. Okay, so here we are getting an expression for mass flux correction as a function of pressure correction. This is the final expression for, in the previous slide I had shown for UP prime and VP prime. Similarly, you can obtain from UW prime and VS prime. And this is for the 4 different phases of the control volume. You can get this mass fluxes, and if you look into this mass flux correction equation, this is very similar to Fourier law of heat conduction, where instead of conduction flux, you have the mass flux corrections, and instead of temperature, you have pressure correction. And instead of minus K, here you have minus delta T. Okay. So in conduction, you have Qx comma E is equals to minus K T capital E minus T capital P divided by delta Xe. So instead of T, here we have P prime. Instead of Q, here we have M prime. So the mass flux correction, so this equation for mass flux correction is a function of pressure correction. I had mentioned during the philosophy that one of the key equation in this topic is mass flux correction as a function of neighboring pressure corrections. And note that this equation is similar to Fourier law of heat conduction. And instead of K, here you have delta T. So I started with prediction of velocity prediction, mass flux prediction, then I had presented the velocity correction and mass flux correction. Finally, I'll present the pressure correction. Now this pressure correction will be presented from the mass conservation law. So we start with the mass conservation law for an incompressible flow. So this is which states that the net mass outsourced and as I mentioned, mass conservation law we apply implicitly. So this is your equation. In this equation, we substitute mn plus 1 is equals to m star plus m prime. So if you substitute that, you end up with, if you take all the prime values on the left hand side and all the star values on the right hand side, you end up with, so this is like mass source from the corrections and this is like a mass source from the predictions. So you get finally end up with an equation that the mass source from the corrections, velocity corrections or the mass flux correction should be is equal to negative of the predicted the mass source, the predicted mass source. This is the predicted mass source and this is like a mass source from the corrections. They have a negative correlation. Now, in the previous topic I had shown you mass flux correction is a function of pressure correction, which is similar to Fourier law of heat conduction. So if you substitute instead of K, I said you have a minus K, you have a minus delta T. And this is expressed in terms of normal gradient of pressure correction, like in conduction is conduction flux is expressed in terms of normal gradient of temperature. So when you use mass flux correction as a function of pressure correction, which I presented in the previous slide, so when you substitute this mass flux correction in terms of the gradients of pressure correction, you end up with this equation. So the left hand side gets converted into like a what you see in a total heat gained by conduction. So this left hand side is this left hand side is like a total mass source from the corrections. So this equation is very similar to steady state heat conduction with the heat generation. So the right hand side you have a predicted mass source. So you get an equation for pressure correction as a function of mass imbalance with a negative correlation. There is a negative sign here. So I have mentioned that there are two equations which are important for this topic. Mass flux correction is a function of pressure correction, which I had shown you in the previous slide here. And in the next slide, I am showing you pressure correction as a function of mass imbalance, which is the second equation. While presenting the philosophy, I have presented this expression as function, but note that here I am showing you a step-by-step derivation of both the equations. This equation right now is not much more explicit in this form. I will show you more explicit form like this in the next slide. So let us suppose you are using an explicit method to solve this iteratively. So when you are using, let us say, Gauss-Seidel iteration, then when you're using a Gauss-Seidel iteration, then normally we scroll through from the bottom left corner. And if you define I and j the way it has been presented in my earlier video lectures, so for any grid point P, when you're doing a Gauss-Seidel based iteration, the west and the south are the updated values, and the north and the east are the previous iterative values. So if I use n as the iteration number to calculate P prime P at n plus 1, so when you want to calculate the new iterative value, note that here n is the iteration number, where n plus 1 is the new iterative value and n is the previous iterative value. When you are using a Gauss-Seidel method, and if you scroll through the loops during iteration, the way it has been presented in the previous video lecture, to calculate the pressure correction at a point P, the west and the south neighbors are the updated or the new iterative values, and the north and east are the old iterative values. So in this equation, PE and Pn have a superscript n, and Pp, Pw, and Ps have a superscript n+1. So I am trying to show you a residual form of the pressure correction equation, which will demonstrate more clearly pressure correction as a function of negative of mass imbalance. So this equation, if you follow certain algebraic steps, it can be converted into this form. I'm showing you the final expression. You can do through pen and paper yourself and check it out. That from this equation, by using algebra, you can convert into this form, where, as I mentioned earlier, n is the iteration number for Gauss-Seidel iteration. And finally, you can get an expression, which is now you can see P prime of the new iteration as a function of the mass imbalance, where this is the mass source from the predicted mass source. This is like the corrected mass source, and this AP is given by this expression. So here I am showing you a much more explicit equation for pressure correction as a negative correlation with the SMP star, which is the mass pressure. Note that this SMP prime consists of all the known values. Whenever you are solving for a point P in a Gauss-Seidel iteration, for west and south, you know the new iterative value. Okay, so this is like a much more, this is called as a residual form of the pressure correction equation. So here I am presenting a residual form. So this is an equation that will be used to obtain pressure correction as a function of mass imbalance. So in the previous slide, I had shown you that we have we started with a fully explicit approach to obtain U star and V star. And from U star, V star, when you multiply with rho density, you got mx star, my star. Using those mx star, my star, if you use this equation and start with an initial condition for pressure correction and boundary condition for pressure correction, you can obtain the pressure correction. Once you obtain the pressure correction, you should have an equation to calculate new mass imbalance, because the iterative procedure that we are using follows an approach from us in a certain iteration. We predict velocities and mass flux, we obtain mass imbalance or mass source, and from mass source we obtain how much pressure we have to tune. Once we tune the pressure, we get new mass imbalance, and from those new mass imbalance we calculate again new pressure correction. So this way our iteration goes on. So in this step we have obtained pressure correction. So in the next slide I will show you from this pressure correction how to get an updated value of predicted mass fluxes. So we will obtain mx star for new iteration as a function of pressure correction. So the mx star and mx, first we will obtain mx prime, my prime, then we will add to the mx and mx star and my star of the previous iteration to get the mass flux for the new iteration. So this is the mass flux correction as a function of pressure correction. So we are obtaining, once we have obtained the pressure correction, in the pressure corrections, once we have obtained, in the next slide, you have to obtain the mass flux correction for the new iterations. Using the new iterative value of the mass flux correction, you add it to the previous iterative value of m star, and you obtain an updated value of the new iterative value of, okay, so this is like a new m star is equals to old m star plus m prime. And you keep doing this till you get a mass source which is close to 0. Okay, so in this slide I am showing you the mass flux correction as a, from once you obtain the pressure correction. So note that the previous slide is like first equation inside the loop. This is like the first equation inside the loop to get the pressure correction. But note that the iteration involved not only this equation, but it also involved these equations for mass flux correction and these equations, because in each and every iterations we are tuning the pressure. After tuning the pressure, we are obtaining the mass flux correction, and from the mass flux correction we are obtaining the new mass fluxes, new mass imbalance, So inside the loop, note that you have many equations. Once you obtain that, then you obtain new iterative value of mass source, new pressure, and if this mass source is close to zero, then you need not do any further iteration. Otherwise, if this condition is followed, then as I say, all the star values becomes n+1. So the new iterative values of pressure, velocities, mass fluxes becomes the true value for the next time step. Otherwise, with this new mass imbalance, you go back and use this equation to obtain pressure correction for the second equation. From the pressure correction, you obtain mass flux correction, and then new mass fluxes for the new iteration, new mass source, and continue this iteratively till this condition is over. If you see other CFD books, they present a methodology where inside the pressure correction loop, they have only one equation, which is this equation, and they solve it the way any iterative method, any equation is solved. So but here the equations, the series of equation inside the loop that I had presented is very closely following the philosophy of pressure correction that I had mentioned. Because while presenting the philosophy of pressure correction, I mentioned that from mass imbalance, you get a pressure correction. From pressure correction, you get new mass flux correction, new mass imbalance. So whatever step by step I mentioned in the solution algorithm while presenting the philosophy of pressure correction in the beginning slide of this lecture, I am following the philosophy and the solution algorithm which was introduced in the initial slide exactly here through the series of equations. So this gives you a better connection between the philosophy and the math that is being followed, that ultimately leads you to velocities and pressure of certain iterations which are obeying the mass balance. Then only they become the true velocity for the next time step. Velocities and pressure for the true next time step. So after presenting the semi-explicit method, where I presented the predictor step and the corrector step, in the predictor step, we had predicted velocities and then multiplied by density to obtain the mass flux predictions. So we obtained U star, V star, MXC star, MY star. And then in the corrector step, first I had shown you the derivation for pressure correction equation, where due to the fact that mass flux correction is similar to Fourier law of heat conduction, it is mass flux correction is exactly proportional to the normal gradient of pressure correction. When you apply the mass conservation law and substitute mass flux correction, you end up with an equation which is very similar to steady state heat conduction with volumetric heat generation, where the conduction term, in this case, you get in terms of the pressure correction gradient, and instead of heat generation, you get a SM star. And there is a series of equations which are used inside the iterations, because we, from the predicted mass fluxes, once you get mass imbalance, you obtain pressure correction, and the new pressure correction leads to new mass imbalance. So whatever is presented in philosophy is exactly followed in the series of derivations that I showed in the previous slides. Now, there are a couple of numerical criteria that I have presented in the previous topic also, so that is presented here also. One is the stability criteria and second is the stopping criteria. So for this case, it's very similar to the criteria that we use in a convection. There are two criteria, one for advection, which is called as CFL criteria. So for pure advection, this is the criteria which have been proposed. So to obtain delta T corresponding to stability, we use the mod of the velocity, U velocity is the mod of the V velocity. And there is a second criteria which is obtained from the conduction or diffusion. This is obtained from advection. This is obtained for a pure diffusion problem. I mentioned in the previous topic that we do not have a formula for a combination of advection and diffusion. We have a formula to obtain the delta T for pure advection and pure diffusion. So we get 2 delta T and we use the minimum of the two. Note that this is a necessary condition, but is not sufficient. So what I mean is that the minimum of the two delta t that you have obtained from here, if you use in a problem, it is not guaranteed to converge in a semi-explicit method. So if it doesn't converge, you have to use a trial and error method. You have to use a slightly smaller value, and if keep doing it till it converges, till you find a delta t that it converges. Now, steady state convergence criteria is, as I mentioned in the earlier topic, we here take the non-dimensional time-wise gradient of the non-dimensional velocity. The non-dimensional rate of change of velocity for u as well as v should be less than or equal to 0. If it's a heat transfer problem, you also have to take the non-dimensional rate of change of temperature. So that completes the semi-explicit method. I started with a philosophy, and using that philosophy, I've shown you series of equations for predictions and corrections for velocities, mass fluxes, and the pressure correction. Finally, I'll present the solution algorithm and an example problem. The first step in any solution algorithm is user input. As I mentioned, that the CFD software cannot be completely automated because there are millions of problems in fluid mechanics, and whenever somebody is using any software, he has to enter certain values which are called as user input. So one of the first thing is that you have to enter, because you only know what is the fluid that you are using. So thermophysical property of the fluid, such as density and viscosity, for a single phase flow, and then you only know what is the geometrical dimension of the problem that you are solving. So this topic is on CFD for problems which are in Cartesian coordinate system. So if you are given a rectangular domain in which fluid flow is occurring, so there are certain geometrical parameters like length of the domain and the height of the domain, which are given here as L1 and L2. These are the geometrical parameters. Then next input is you have to enter the maximum number of grid points in X and Y direction. For a Cartesian coordinate system, once you enter this, then the Cartesian grid can be generated. If it's a uniform grid, then it becomes much simpler. Then there are certain parameters corresponding to initial condition. Here for velocities and pressure, you have to enter the initial condition. Now there are certain boundary conditions parameters that you need to enter, which I'll mention a little later. Then you have to enter certain governing parameter. Most of the time, when we do simulations, we try to do simulation in non-dimensional form. So we enter the parameter in a non-dimensional form, such as Reynolds number in the example problem that we presented below. Finally, user input is showing the steady state convergence tolerance. So you have to enter the steady state convergence tolerance. Note that even if you are following a semi-explicit method, there are two loops. One loop is for pressure. So for an iterative solution of pressure correction equation, you have to enter the convergence tolerance. So there are two convergence tolerances. One for convergence of pressure correction, which is epsilon, and this epsilon t is for the steady state convergence. So there are two convergence tolerance. Epsilon for pressure correction, epsilon st for a steady state convergence. After presenting the user input, the next step is you have to calculate certain geometrical parameters. For a uniform grid, geometrical parameters are the width and the height of the control volume, delta x and delta y. Then you have to enter the initial condition for the velocities and pressure, and also for the predicted velocities. You have to apply the boundary condition for the velocities, and note that while applying the initial condition and boundary conditions, you not only have to apply for u, you have to also apply for u star and v star. Then the velocity and pressure at the present time step is considered as the previous time step values, which we have been doing in previous topics also, as the computation needs to be continued further for the computation of their values for the present time step. Thereafter, you calculate the time step from CFL and grid Fourier number criteria that I presented earlier, and use the smaller values. Note that you are using a semi-explicit method, so there is a time step restriction. Then the next step is prediction of u velocities and mass fluxes. Note that we predict not only the velocities but also mass fluxes. I presented the equation corresponding to those in earlier slides. compute various fluxes, mass flux, advection flux, and diffusion flux for the momentum preservation at all the phase centers, and you for the U control volume and V control volume, and predict basically U star and V star. Then you calculate total mass outflux. First, you calculate the total outflux of advection, diffusion, and predict the velocities, and the mass flux for the next time step. So you predict U star and MX star, V star, and MY star at the internal grid points. For non-Dirichlet boundary conditions, as I mentioned in the previous topic also, you have to apply the boundary conditions separately to update the U star, V star, and compute MX star and Y star. So to compute the mass source. So note that this slide represents the predictor step. And if the mass source is 0, then the whatever star values which you have obtained becomes the true velocity for the next time step. And then you need not follow the correction step. You can go directly to the 17.4. But for most of the cases, this condition is not obeyed. Then you have to go to the next step, which is a correction step. Before that, when you start the corrective step, you have to apply the initial condition for pressure correction. Normally we take P prime is equals to 0. Then you have to apply the boundary condition for pressure correction, which I'll present a little later. Then you have to compute first the pressure correction. I mentioned that once you go to the corrective step, you have series of equations. So this is the first equations. And then from the pressure correction, you have to obtain the mass flux correction and the updated values of the predicted velocities and the predicted mass fluxes. So along with this equation, you have this equation, and then you compute the updated values of mass source and the pressure. And after each iteration, you check for this mass sources after every iteration until it approaches towards 0 or epsilon. Then if it is not, then you have to go back to step 9. So this is your iterations goes on, and inside this iteration, you have series of equations. First for pressure correction, then for mass flux correction, the function of pressure correction, then updated value of M star, U star, updated value of new iterative value of mass source, and then you finally check. So here we are following all the steps that was presented in the philosophy. So finally, if once you get the converged, when the mass source approaches towards 0, when it converges, then the updated value of pressure and mass flux is the star value becomes n plus 1. Thereafter, once you've obtained the true velocities and true pressure for the next time step, you have to check for the steady state convergence. If it is achieved, then you can stop. Otherwise, you have to go back to step 4 for the next time instance execution. So if it is converged, you can stop and process the steady state results for the analysis of CFD problem. In an inherently unsteady problem, the condition in the previous step, this condition will never be obeyed, and a different stopping criteria is needed. So after presenting the semi-explicit method and its solution algorithm, you can develop your own computer program. However, there are a lot of implementation details which are like nuts and bolts to develop a product. In this case, it corresponds to the data structure and the loops, which are not presented in this video lecture, but you can find the details in the companion book, so which can help you much more in developing the working code for this problem. So if you develop your own computer program, so as an example problem, I am here presenting one of the classical test problem for a Navier-Stokes solver, which is called a lid-driven cavity flow. So this is a problem where, let's suppose you have a box and there is a cavity, which is this is a let us like rectangular box where the top wall is moving like a conveyor belt from left to right, and so this is the left wall, this is the bottom wall, and this is the right wall. These are stationary, and the top wall is moving like a conveyor belt. So when the fluid which is in contact with the top wall, it moves along the wall, but at the corner it cannot go out, so it turns. And when it comes down, the bottom fluids are stationary, which tries to resist this motion, so it turns further. So there is a set. This sets up a clockwise rotation of the fluid inside this cavity. This is right now it's a square cavity which we are considering. You can also consider it as a rectangular cavity if L1 is not equal to L2. But if L2 is both are equal, then this is a square cavity. This is a problem corresponding to the squarely driven cavity flow. And this is one of the classical test problem or benchmark problem in for Navier-Stokes solver. And the boundary condition that is considered for this is I'll present here in a non-dimensional form. The length scale here is taken as the length of the cavity. The lead velocity is taken as the characteristic velocity. And the Reynolds number is defined as rho multiplied by lead velocity multiplied by the length of the cavity divided by the dynamic viscosity. And here I show you the non-dimensional, the initial condition where non-dimensional velocities, pressures are taken as 0. These are the boundary conditions for the stationary walls. So left wall, right wall, bottom wall stationary. So the velocity u and v are 0. Later on, here the boundary, we also need to use the boundary condition for pressure correction. I had shown you earlier an equation for mass flux correction as a function of normal gradient of pressure correction. So on any wall, whenever you consider a solid wall, such as in this case, for any solid wall, you are given the velocities. So once you know the velocity corrections are 0. Once the velocity corrections are 0, mass flux correction is 0. So when the mass flux correction is 0, then the normal gradient of pressure correction is equal to 0. So you can see on the vertical wall, you have a del P prime of del X. And on the horizontal wall, you have del P prime by del Y is equal to 0. So this boundary condition is basically the normal gradient of pressure correction is equal to 0. So as I mentioned, this mass flux correction is similar to, as I said, Fourier law of heat conduction. So this boundary condition is similar to like an insulated boundary condition, because in a solid surface, if you want to apply the pressure correction boundary condition, it is analogous to the way you apply the insulated boundary condition in a conduction problem, where in a, let's suppose, left wall, right wall in a conduction problem will be insulated, you have del T by del X equal to 0. If bottom wall is insulated, you have dt by dy equals to 0. So here in a solid wall, the fact that you are given the normal velocity, and if something is given, correction is 0. So the velocity correction is 0, mass flux correction is 0, and so the normal gradient of pressure correction is 0, which is shown here as a boundary condition. This shows the boundary condition for the top wall, where this capital U is a small u divided by u0. So at the top wall, u is u0. So u0 by u0 is 1. So the non-dimensional velocity is 1. At wall, v is 0. And this is the normal gradient of pressure correction, which is also applied at the top wall. Here again, note that you are given the value, the normal velocity for this horizontal wall is v, which is equal to 0. So when v is 0, v prime is 0. When v prime is 0, my prime is 0. And when my prime is 0, del p prime by del y is equals to 0, which is used here as boundary condition. In this slide, I'm showing you, I'll show you the 3 different control volumes. The yellow control volumes on which the energy conservation law is applied. This control volume is used to apply the mass conservation and energy conservation. This yellow control volume is called as a main control volume or a scalar control volume. So in this control volume, if you are applying for mass conservation, then calculate mx on this grid points, which are shown here by green squares. And if you are applying the energy conservation law on these green squares, you will calculate qx and hx, which are conduction flux and enthalpy flux. Note that for the control volume that I am showing here, there are 25 yellow circles or 25 yellow control volumes in this problem. Whereas if you see the green square, there are 6 in x direction and 5 in y direction. The yellow circles are 5 by 5. The green squares are 6 by 5. So the loop for that I presented earlier also, because in earlier topic on computational heat conduction and convection, these yellow circles were pixels for temperature, and then green square was for Qx. So I had mentioned, so the loop that we have used for Qx is presented here to calculate you can calculate the enthalpy flux, conduction flux, and also used to calculate the mass fluxes. And we are following a convention where the running indices for the positive phases correspond to that of the control volume on which it lies. So the fluxes, the running indices corresponds to on the positive phases. So here it is I comma j. The flux here will be I minus 1 comma j, because this I minus 1 minus the flux on this phase is a positive phase of ti minus 1 comma j. So the loop for the green square is 1 to Imax minus 1. Imax is 7, so it is 1 to 6. So you have 6 green square and in the x direction and 5 in the y direction. So in the I direction, there is increase by 1. When you consider the horizontal phase center, which are shown here by red triangles. Now the red triangles are 5 in the x direction, 6 in the y direction, and its loop is I is equals to 2 to Imax minus 1 and j is equals to 1 to j max minus 1. Note that in a staggered control volume, the control volume used to apply the X quantum conservation is different. So note that the mass conservation is applied on 5 by 5 yellow control volume. The X quantum conservation law is applied on 4 by, when I say 4, I test 4 green control volume in the X direction, and you have 5 green control volume in the Y direction. This is the first, second, third, fourth, and fifth. So you have, whereas if you look into the yellow control volume, they are 5 in the x direction, 5 in the y direction. But the green control volumes are 4 in the x direction and 5 in the y direction. Note that we are not bothered about this half control volume because this value we obtain from boundary conditions. So we apply, when you consider a staggered control volume for the figure that I am showing you here, these are the control volumes for X momentum conservation. Now, the loop for the green squares, because to calculate UP star and UP prime, since they are 4 instead of 5 here, there is here you have in the x direction 1, 2 to I max minus 1, but you have here 5 yellow circle in the x direction, but here you have 4 yellow circles. So note that the loop changes from 2 to I minus 1 when you have 5. So for 4, this becomes 2 to I max minus 2. So this is 2 to I max minus 2. And you have 5 in the y direction, so it remains same. Now for this control volume, also note that when you apply to this green control volume, you have to calculate X momentum flux, you have to calculate viscous stresses in the X direction. Now to do that, let us suppose you are obtaining the viscous fluxes in the X direction and momentum fluxes in the X direction, that you will calculate on this yellow squares. Okay, so for the loop for this yellow squares, which is 5 in the x direction and 5 in the y direction, the loop is we are following the same convention that for positive phases we have the same running indices. So for the vertical phase center of the green control volume, the loop is shown here, and for to calculate the fluxes for the X momentum conservation or at the fluxes in the y direction, this is the loop which is used. This is for X momentum conservation. So you can note that when you compare this loop for the variable and the fluxes for the main control volume and the momentum conservation, there is one difference between the loops for the variable and fluxes, which is shown highlighted here, that here you have Imax minus 1 for the flux as well as variable, whereas here you have Imax minus 2. This is extremely important for you to note when you are developing your computer program, because it's very likely that if you are not careful enough, you can do mistakes. Note that CFD is a subject which gives you approximate solution, but when you are developing a product, you are not allowed to use any approximation. Each and every step of yours should be nothing less than perfect. Each and every line of your computer program has to be exact, not approximate. These are the control volumes, V control volume, in which you apply the Y momentum conservations. Now you can see that the red control volumes are 5 in the X direction, 4 in the Y directions. So here now, here it was 4 by 5 for X momentum, but for Y momentum it is 5 by 4. So now here when you see the loop, instead of I minus 2, you have J minus 2. And when you consider the fluxes, The fluxes are shown here. This is for the when you want these are calculate the fluxes for y momentum conservation in the x direction. These are shown by the magenta color triangle, and this orange color triangle is used to calculate the fluxes in the y direction for while applying the y momentum conservation. So here I had shown you the loops which are extremely essential for developing the program. This corresponds to figure 9.9 of the companion textbook. And I wish and hope that this will be very useful for you for developing the program. As I mentioned earlier, more implementation details which are essential to develop the right computer program for this topic. You can refer the book that can greatly help you to successfully completely get the correct program and test the program on the problem that I'm presenting here. As I mentioned that for this, we have Jmax minus 2, which is different from the main control volume. Finally, I am presenting the boundary condition that you have to consider for the lid-driven cavity flow problem. Although I had introduced earlier, and here I am presenting the mostly boundary condition which are 0. And the pressure correction boundary condition, you have a normal gradient is equal to 0, which is like an insulated type of boundary condition. So you can see that they are presented as like when you have an insulated type of boundary condition, the value at a boundary is equal to the border value. So for pressure correction, we have a normal gradient is equal to 0. So this is the discrete form of the normal gradient pressure correction boundary condition for the left, right, and bottom wall. And the velocities are 0 because these walls are stationary. Now, when you go to the top boundary, you have u velocity is equal to 1 and v velocity is equal to 0. Note that these velocities are non-dimensional velocity. Now I'll present that once you develop a computer program and when you run it, then you can plot. There are two types of plot that I will show. There are certain 2D plots which will be presented like velocity vector plot, the streamline plot, and the pressure contour plot. And if you want to compare your results, there is certain data which is available in the literature for this problem, which is widely used for testing your code. So once you run your code, if you store the variation of u velocity along the vertical center line of the cavity, and if you store the variation of v velocity along the horizontal center line of the cavity for various grid sizes. So on the cavity, there are two center lines on which if you store the data, you store horizontal velocity on a vertical center line, vertical velocity on horizontal center line. Then there are certain data which is available corresponding to this center line, with which you can compare the results that you obtain from your computer program with the published results and check whether they are matching for testing. So for the present algorithm that was presented, a computer program was developed, and this is the result which has been obtained. So this is figure 9.12 of the book, which corresponds to CFD application of semi-explicit raised 2D Navier-Stokes solver on a uniform staggered Cartesian grid for a lid-driven cavity at a Reynolds number of 100. Results have been obtained on a grid size of 42 by 42. These are steady state results. This is for velocity vectors. So vectors, the velocities are represented here by vector plot. You can see certain arrows with certain scales. And on figure B, the pressure contour is overlapped with the streamline. So the red color of pressure corresponds to a non-dimensional value of 1.2. The dark blue corresponds to minus 0.6. So the color here is showing the pressure variation inside this cavity. And these lines are the streamlines. So the flow this gives you the direction of so it's like a circulating flow, which I mentioned. And so the flow rotates the clockwise direction where the center of rotation is this. So this gives you the 2D plots for the velocity vector, pressure contour, and the streamline. And finally, for testing, we draw certain 1D plots where this figure shows the variation of u velocity on a vertical center line, vertical center line y coordinate is varying, which is shown here in y-axis, and for v velocity it is shown on the horizontal line. And so you can see that the symbols, the square symbol for variation of u velocity on vertical center line, this has been reported by Ghia et al. So this is the data which is very widely used in literature. From the computer program was run on various grid size 7 by 7, 12 by 12, 22 by 22, and 42 by 42. And you can see that as the grid is refined, the solution asymptotes to the correct solution, and on a grid size of 42 by 42, the presently obtained results matches very well with the published results. This is for variation of u velocity on vertical center line. Note that the u velocity is negative in the lower half because the fluid rotates in the clockwise direction. So you can see these are like negative velocities. Also on the lower half, you have a negative velocity because when you have a clockwise rotation, on the upper half you have a u positive, but in the bottom half you have a u negative. Whereas when you look into the v variation of vertical velocity on a horizontal center line, on a horizontal center line near to the left wall, the v velocity, if you have a clockwise rotation, v velocity is positive. So these are the positive v values. And near to the right wall, you have a negative v velocity for clockwise rotation. So here again, you can see when the grid size is increased from 7 by 7 to 42, the results obtained from the computer program asymptotes to the correct solution. So this completes the testing of the code. So this lecture presents the semi-explicit method, solution algorithm, and finally a test problem used to compare the results obtained from whatever have been, if you develop your computer program from the solution algorithm that is presented earlier, you can also test your program with these results. With this, I have come to the end of this lecture. You can get more details in the chapter 9 of this book on Introduction to CFD Development Application Analysis. And this is the website from which you can get the supplementary material. Thank you for your attention.